Okay, now we're doing number 4. You might want to get comfortable because this one will take a while. The first part is asking you find intervals in which a function is decreasing. So it would help to know the derivative. And the reason why that would help to know that, because if f prime x is negative, remember that means when you're going to have tangent lines with a slope that is negative, that would imply that you have a falling function or decreasing function. So if I do this right now, f prime x should equal negative 1/6 times 6 times x to the 5th power plus 2/5 times 5 times x to the 4th power. Clean it up. You should get negative x to the 5th power plus 2x to the 4th power. Now to find out where it's actually decreasing, let's set the derivative equal to 0 and find our critical points. So you have, I could take, say, negative x4. I have x minus 2. So that means that x would equal 0 or 2. Now, we look at the intervals to the left of 0, in between 0 and 2, and to the right of 2 to see how the derivative is changing. If we do see a sign change, or sorry, actually I'm thinking about something else, sorry. If we do see an interval where the derivative is negative, then we know that that's going to be decreasing that interval. So we'll do a sign chart. And then using Christmas colors, we'll test values in these intervals. So if I were to plug in negative 1 to my derivative, you will find that you will get a positive value, because negative x to the 4 is still going to be positive. Sorry, still going to be negative, and negative 1 minus 2 is negative. 2 negatives gets you a positive. If you plug in 1, we'll still get the same thing. And if I plug in 3, it will be negative. So clearly it's decreasing from 2 on to infinity, according to our sign chart. For part B, any local extreme values. So in a way here, it's kind of like we're doing the first derivative test. So we know f prime x equals 0 at x equals 0 and x equals 2. But no sign change for f prime x at x equals 0. But there is one at x equals 2. F prime x changes from plus to minus. So that implies that we're going to have a local max. Or relative max, however you want to call it. So we would write it like this. And first of all, let's find what f of 2 is. If you punch in your calculator, you would get 2.133. Remember, 3 decimal places. So you'd say that there is a local max of 2.133 at x equals 2 because f prime x changes from positive to negative. For part C, where it's concave up, so now we need to do a second derivative. If you work that out, remember earlier our first derivative was negative x5. Where is it at? Yeah, it was this. Negative x5 plus 2x4. So second derivative would be negative 5x4 plus 8x cubed. We'll need to see the intervals where it's concave up and concave down, so we have to first set their second derivative equal to 0. And you can factor out a negative x cubed. Let's get 5x minus 8. So 0 or 8/5 is where we could see changes in concavity. So again, we'll do another sign chart. And we'll test points. Go back to red. We'll test 1, 2, and negative 1. Into the second derivative, we plug it in. If you plug in negative 1, you should get a negative value for the second derivative. Positive if you plug in 1. And back to negative if you plug in 2. So clear it's concave up between 0 and 8/5. And keep in mind we want to use open parentheses here. Or sorry, I'm totally getting things mixed up here. We want to use parentheses, not brackets, because at 0 and 8/5, it's really not concave up or concave down. It's basically that's when you have a point of inflection at those values. Which brings me now to the next part, part D, the x-coordinates, which is a point of inflections. So clearly at x equals 0, since f double prime of x changes, or you could say just changes sign, doesn't really matter how it changes. And x equals 8/5 for the same reason. Okay, and then lastly, for part E, you're asked to find absolute extreme values in the closed interval from -1 to 3. Well, we already know that we have a local max at x equals 2. So let's actually figure out what the y values are at -1 and 3. If you were to plug in -1 to your function, you should get negative 0.567. And if you plug in 3, you should get 24.3. Okay, now here's what we need to understand. Looking back at our sign chart for the first derivative, from -1 to 0, clearly derivative is positive, right? So it's an increasing function from -1 to 0. So that makes this a local min, since f prime is positive from -1 to 0. And then for f of 3, if we take a closer look at that one, on that interval from 2 to 3 in the first derivative, we see that it's a decreasing function because the derivative is negative. So it makes that a local min as well. And remember all those corollaries you talked about depending on left or right endpoints. So for a left endpoint, if after the left endpoint the derivative is positive, we expect it will be a local min. If it's negative, then it will be a local max. It's the opposite situation for the right endpoint. If the derivative is negative to the left of the right endpoint, then of course it's going to represent a local min when you get to that right endpoint. But if it was positive, then it would be a local max. So clearly 24, that's negative 24.3, my apologies. Clearly negative 24.3 is lower than negative 0.567. So it makes that an absolute minimum. So we have absolute minimum, and there was no local minimum points we found in part B. So the lowest possible point would be negative 24.3 at x equals 3. And we have an absolute max because the endpoints didn't provide any local maximum points. So we go with what we had in part B of 2.133 at x equals 2. So that concludes number 4.